Okay, so this is chapter 2 of the matrix algebra book, matrix operations book. Okay, this is chapter 2 of the matrix operations book. So simultaneous linear equations. So here we are going to see how we can use the matrices to solve the system of equations. A system of m linear equations in n variables is a set of equations of the form given below. Here the x1, x2 up to xn are the unknowns or the variables. So we have n variables, and then aij's and bi, these are known quantities. The system for this solution is a set of values for each unknown. So there are n unknowns, so n values that satisfy all these equations of the system. So the system is said to be consistent if solution exists, and it is said to be inconsistent if the solution does not exist. So how about we convert this system into matrix notation? So we can write it in matrix notation like this: Ax is equal to B, and x is actually what I would like to use is with the vector. So Ax is equal to B. You can, instead of this, we can write it like that. That's how in the DE book you will see. So this I will call it, instead of big X, I am calling it the vector X. Similarly, this I call it the vector B. Now the A matrix is the coefficient matrix, and we have to do something called augmented matrix. What we do with the A matrix, we put this B, column vector B, along at the end of the A matrix here. So this is the augmented matrix, and I put a line here just to distinguish that on the left is the A and the right is the B. Now we say the system Ax is equal to B is consistent if and only if the rank of A is equal to the rank of AB, the augmented matrix. So if the rank of these two is same. And what does it mean by the rank? Rank is the number of non-zero rows in a echelon form of the matrix. Okay. Now another theorem: denote the rank of A as k and the number of unknown as n. If the system is consistent, means if the system has solution, then there will be actually some arbitrary scalars, or there will be some, we call them free variables. Now if B is equal to 0, the B vector is the 0 vector, then the system is called homogeneous. And if the B is not 0, so if at least one entry in the B vector is not 0, then the system is non-homogeneous. Now homogeneous systems are always consistent, means they always have a solution, because the 0 vector is the solution, and it is called the trivial solution. So if again the rank of A is k and the number of unknown is n, the homogeneous system Ax is equal to 0 has a trivial solution if and only if n is not equal to k. And that's what we saw in the previous similar kind of argument or statement in the previous theorem. So now we revisit the elementary row operations. There are 3 of them. Remember that we can interchange any 2 equations, so we can interchange any 2 rows of the matrix. Multiplying an equation by a non-zero scalar is the same thing as multiplying a row of a matrix by a non-zero scalar, and adding to one row a scalar times another row. So these are the 3 applications, and when we apply these 3 operations to the system of equations, is equivalent to applying the elementary row operations to the augmented matrix. So how does the Gaussian elimination work? This is also called a row reduction algorithm, and it's used for solving the system of linear equations. And it consists of a sequence of row operations on the corresponding matrix of coefficients and the augmented, the B augmented. This method can also be used to compute the other things like rank of a matrix, determinant of a square matrix, and the inverse of an invertible matrix. This is something you will see later. Now the method is called is named after the mathematician Carl Friedrich Gauss. He lived from 1777 to 1855. Now to perform a row reduction on a matrix, we have to use the elementary row operations. So the first thing you have to know is how to write the augmented matrix. So here, how to convert it into the the matrix form. So this is the matrix form of the equation, and where A is this, X is this, B is that, and the augmented matrix, this is what it is. So it's easy to write the augmented matrix. Now from the equations you can write the matrix, but also from the matrix you should be able to read the equation. So how do you read it? Remember, this one will be x1. Remember, this first column will be the coefficients of x1, second will be the coefficients of x2, third will be the coefficients of x3, and then if you see this line and then another column, then this is the B column, the entries of the B vector. So this is going to be coming on the right side of the equal to sign. So we can now write the equation from the first row, x1 plus 1 half x2 plus 0 x3 is equal to 5. So if there is a 0, it means the coefficient of that variable is 0. Looking at the second equation, I get 0 x1 plus 1 x2 plus 2 over 3 x3 is equal to negative 1. And reading the last equation, we see it gives us 0 is equal to 3. Now this is false. This cannot happen. So if you end up getting something like this, it means system is inconsistent. It means it has no solution. Okay. So looking at the next example, so it's very similar to the previous one, just that I have this last line different now. So from the last line, you see we have x3 is equal to 3. So 1 times x3 is equal to 3. Now second line gives you x2 plus 2 over 3 x3 is equal to negative 1. So what we do now, we can substitute this value of x3 here and get the value for x2. So this gives me x2 plus 2 over 3 times 3 equals negative 1. So we get x2 is equal to negative 1 minus 2, so negative 3. So we got x3, x2, and now x1. So the equation for x1 is x1 plus 1 half x2 is equal to 5, which means x1 is equal to 5 minus 1 half x2. Well, x2 is negative 3, so we get 5 minus negative 3 over 2, so or plus 3 over 2, which gives me 13 over 2. So the solution, you can write it separately like this. x1 is 13 over 2, x2 is negative 3, and x3 is 3. Or you can write it in the vector form as variables give you the solution. Okay, looking at number C. So you should be able to read, now the last is just giving you 0 is equal to 0, so that doesn't count, or that doesn't give us any information. But the second row gives us x2 equals 3. So how do I know it's x2 not x1? Well, remember, you can write your these x's on the top, xi's. So first column is going to be the coefficients of x1. Second column is the coefficients of x2. Now this is not the coefficients of x3 because we see this bar, so it is the augmented matrix. So this last column will be the B column, which means these are the values that are going to come on the right side of the equation. Okay, so x2 is 3, and then from the top we get x1 plus 2x2 is equal to -1, which gives me x1 is equal to -1 minus, from here I'm left 2x2. So -1 minus 2 into 3, we get -7. So x1 is -7, x2 is 3. Or you can write in vector notation. So that's how you write your solution. Okay, looking at number D. So last is giving us 0 is equal to 0. Again, no point in writing that. Let's put our x's. So it means there are 3 variables, and so initially we had 3 equations, but now they reduced to, in the echelon form, we see only 2 equations basically. So what has happened to the third one? Well, this is where we are getting the what do you call it, the free variable. Or note here, as mentioned, so remember the number of non-zero rows is called the rank. So the rank of this matrix is, or of this system is 2. And number of unknowns is, so 2 or k, remember, and n is the number of unknowns, so n is 3. So there is a difference. The 3 and 2 are not same. So we had this theorem that if k is not equal to n, then we will get free variables. So there are some free variables. So here we notice, how do we recognize the free variable? So remember the pivot. So this is called the pivot. So if we had 3 pivots, we would not get a free variable, and we would be able to get a value for each of our unknown. But here, there is no pivot in the third row and third column, so this is the free variable. So x3 is the free variable. Sometimes in some books they say let x3 equal to t, some parameter t. So then from the second equation you can write x2 plus 2 over 3x3 is equal to -1, or x2 is equal to -1 minus 2 over 3x3, and then from the first equation you can write x1 plus 1/2 x2 is equal to 5. But when we have a free variable, all the non-free variables, which are called the basic variables, by the way, so the ones which are not free are called the basic variables, and we must write the basic variable in terms of the free variable. So here I can get from here x1 equals 5 minus 1/2 x2, but we should get it in terms of x3. So I will replace the value of x2 here. So I get x1 is equal to 5 minus 1/2 times -1 minus 2 over 3x3. Now simplify. 5 minus, actually it becomes 5 plus 1/2 plus 1/3 x3. So x1 is 11 over 2 plus 1 over 3 x3. So now writing the solution. So I'll put them in order or put them in a vector. So I'll show you how to write it as a vector. And so x bar, so you write x1 and x2, x3, right? So what is x1? It is 11 over 2 plus 1 over 3 x3. x2 is -1 minus 2 over 3 x3, and x3 is just x3. We could also have used the t here, so we could then write it like this, and this will be x1 will be 11 over 2 plus 1/3 t. So now we can put it here in place of this. We can put t here. So now you can see this can be split into two vectors, the sum of two vectors. 11 over 2 minus 1 and 0, because there is no constant term in the third one, plus 1 over 3 x3, -2 over 3 x3, and then last one x3. So we can actually take out the x3 common. So it can be written as 11 over 2 minus 1, 0, plus x3 times 1 over 3, -2 over 3, and then 1. So this is called the parametric form of the equation. Okay, now looking at number E. So we see this is already in the echelon form, and notice we have one pivot here, and that's all. This is not a pivot because this is not the leading or the first non-zero term from the left. So we have only two of these, so it means this first one is x1, this is x2, x3. There are 4 variables. So x3 and x4 are free variables. So these are free variables. Now, as I mentioned before, if you want, we can say let x3 be t and x4 be s. Or you can take as x3 to be s and x4 to be t, doesn't matter. Then instead of x3, x4, we can write our vector in the end in terms of s and t. So from the first equation, we get x1 plus 1/2 x2 plus x3 plus 4x4 is equal to and plus -4 over 3. Okay, I forgot this. Plus 0 times x3 minus 4 over 3 x4 equals 5. So this will go away, and x2 will be, we can get x2 from the second equation, but this one I'll give you x1 is equal to 5 minus 1/2 x2 plus 4 over 3 x4, and instead of x4 I can write t, and if we have x3 we will write so x3 is t and x4 is s. Okay, so let me write x2 plus 2 over 3 x3 plus 1 is equal to negative 4. 1 x4. So x2 is equal to 4 minus 2 over 3 x3 minus x4, or x2 is equal to 4 minus 2 over 3t minus s. Now we have to take this and plug it in here. So x1 is 5 minus 1 half times 4 minus 2 over 3t minus s, and then plus 4 over 3s. So combine 5 minus 2 plus 2 over 3t plus 1 half s plus 4 over 3s. So it gives me x1 equals 5 minus 2 is 3, 3 plus 2 over 3t plus 14 over 6, actually 3 plus 8, 11 over 6s. So you can write your answer as x equals x1, which is 3 plus 2 over 3t plus 11 over 6s. x2 is 4 minus 2 over 3t minus s, and so x1, x2. Now x3, that is just t, and x4, that is just s. Now we split into vectors with the common, with the common s or t or constant. So the constant one will be 3, 4, and we do not have any constant terms in the third variable and the fourth variable. So 0, 0. This is the vector with constants plus. Now we can write with the t. So 2 over 3t, negative 2 over 3t, and then t, and then 0. So in place of t, I will write 1, and I can factor out the t. And then plus, same thing we do with the s. So 11 over 6, negative 1, 0, 1 times s. So this is your vector x. So I'll stop here and do the next examples in the next video.